Complex technology systems are large networks composed of multiple highly interconnected technologies, such as electrical power grids, telecommunications networks, or transportation networks. But let's first talk a bit about technology itself. Of course, the development of technology is one of the oldest human activities, and some would say it's what defines us as distinct from other creatures. Throughout history, we've used technology to automate the processes required for our subsistence, thus overcoming the physical constraints imposed upon us by our natural environment. The application of modern science to the engineering of technology during the Industrial Age resulted in a relatively systematic and scalable set of technologies, based upon the use of petrochemical energy and produced through the centralized mass production process. These industrial technologies were developed within the context of the centrally controlled infrastructure systems of the modern nation-state, and were designed according to a limited set of factors, governed by the logic of industrial capitalism and the need to provide for a modern mass society. By the turn of the 21st century, major trends such as the rise of globalization, sustainability, and information technology are working to reshape our industrial technology systems into highly interconnected and interdependent networks. Economic globalization has resulted in the deregulation of infrastructure, as private corporations are dismantling the once state-owned and vertically integrated systems that were largely confined within national borders and converting them into multinational networks. This is resulting in a landscape with a more fractured and complex set of actors. Telecommunications is a classical example of this. Once run by national operators, it is increasingly converging upon the global network of the Internet, where multiple providers deliver multiple diverse services. In such a world, no one centralized coordinator can fully control or govern the system. The rise of sustainability adds a whole new set of factors into the engineering of technologies. On the micro level, alternative technologies are creating bottom-up, distributed solutions with the advent of such technologies as 3D printing and solar cells that counteract the traditional top-down, centralized design to infrastructure systems. IT is networking our technologies, making them smarter and capable of adaptation. The so-called Internet of Things is set to transform the technology landscape in the coming decades, as we are rapidly developing platforms and networks through which technologies interact, adapt, and self-organize to find optimal solutions. It is within this context that we can talk about complex technology systems, as increasingly our technology becomes part of dense, multidimensional, interdependent networks that exhibit the classical properties of complex systems, such as nonlinear behavior or the so-called butterfly effect within supply chains and electrical power grids. In these highly interconnected networks, small events can rapidly propagate through the system to create disproportionately large effects. Or self-organization, as new IT-enabled technologies like smart power grids allow consumers to analyze and adapt their power consumption in response to varying prices, thus helping to optimize the system's load balance and overall efficiency. Self-organization can also lead to emergent behavior. Traffic jams are classical examples given of this. By understanding how these local-level interactions give rise to macro-scale patterns, we can better engineer desired outcomes. The question then turns to, how can we model these systems using the tools of complex systems theory? Systems theory and the model of a system has long since been used by engineers as a key tool for analyzing the inputs and outputs to technology. In the advent of sustainability, systems theory is becoming increasingly used to model and ascribe quantitative values to the material and energy efficiency of large socio-technical systems, such as cities, corporations, and whole economies. Network theory is another tool used. By looking at these technology systems as networks, we can use network theory to analyze their topology, see how centralized or distributed they are, measure properties such as resilience or criticality, and better understand the linkages through which failures propagate. Agent-based modeling is another method used to simulate the development of these technology networks as they evolve over time. Agents, that can be companies, policymakers, or consumers, are endowed with simple rules and left to interact to see what patterns emerge. We are only just beginning to apply the tools of complexity theory to the modeling and managing of technology. But as the technology systems become increasingly complex and networked in nature, it is proving increasingly relevant to gaining a more coherent understanding of our engineered environment.